problem here, interconverting Kc and Kp. So same reaction that we were talking about, the NO2 dimerization, right? So let's write that down. Two NO2s in the gas phase are in equilibrium with N2O4 in the gas phase, all right? And then we noted that Kc equals N2O4 all divided by NO2 squared. And you notice here we've got several experiments that were done using molarity. So let's first calculate Kc. So I'll write a new column right here. And we'll just do this twice. I'm not going to do this all 4 times because hopefully we see by now that all 4 of these should give me the same result. So for example, for experiment number 1, that's going to be 0.00139 all divided by 0.0172 squared. Okay, so let's calculate that. 0.0139 divided by 0.0172 squared equals. Okay, great. That's not quite what I was expecting based on my cheater notes. Let me see what I did wrong. 0.00, I think I might have forgotten a 0, 139 divided by, where is it? 0.0172 squared equals, okay, so my cheater notes here told me I was supposed to get 4.70. Okay, so we recognize that one's 4.70. Let's do the next one just to double check. So that's going to be 0.00280 divided by 0.0244 squared equals, hallelujah, look at that, 4.70. Okay, so pretty good bet that the other ones are going to be 4.70. So now how do we interconvert this? Well, we know our formula is Kp equals Kc times RT raised to the delta N power. So first we've got to calculate that delta N power, okay, the change in stoichiometric coefficients. And if you recall, it's going to be the sum of the stoichiometric coefficients of the products. In this case, that's just 1 minus the sum of the stoichiometric coefficients of the reactants. And now in this case, we don't have to add it up. It's just 2. There it is, right? So now 1 minus 2 is -1. It's important we preserve the sign on this thing, okay? And so now let's see here. Okay, so we can say Kp equals, so we know that Kc is 4.70. And so now I'm going to use brackets just not to denote molarity, but just to denote, mathematical operation. So my value of R is 0.08206. I'm going to drop writing the units just for ease. And then now we need the temperature of the reaction. So here we can see this says data for the dimerization of NO2 at 100 degrees. So this data was all taken at 100 degrees Celsius. Well, this has to be in Kelvin because our gas constant units have Kelvin. So hopefully, quick math, you remember that 100 degrees Celsius, if I want to convert that to Kelvin, I add it to 273, right? So that becomes 373 Kelvin. So we'll put that down there, all right? And then now this whole thing is raised to the -1 power, okay? All of those constants are raised to the -1 power. So let's go ahead and calculate this in chunks. 0.08206 times 373 equals, and there's several ways I can do this raised to the -1 power on this calculator. If you recall, when you raise something to the -1 power, it's like flipping it, right? So in other words, I could, raise this to the -1, or I've got this handy button right there, that 1 over x. That's the same as raising something to the -1 power. So let's push that button. So now I just flipped it. And then now I'm just going to say times 4.7 equals, okay, good. And according to my cheater notes, that's the right answer. So my KP is 0.154 with 3 sig figs. Okay, so now this is important to note, all right? If we did this experiment and in this data table, it was all partial pressures and atmospheres, okay? We would have gotten to this KP value, the 0.154, we would have just got that directly from the partial pressures, okay? And then, of course, we could have used this formula to actually convert it to Kc, right? We could have divided this RT delta N power over to the other side. However, in this set of data, we were given concentrations in molarity, which gave us Kc, all right? So no matter what the initial concentrations are, this Kc value will work out to be 4.7. Of course, now that's at 100 degrees because as you've seen me allude to, the temperature matters for the equilibrium constant. But if we were to do this in atmospheres, right, in several different experiments with different starting amounts, all of those experiments would give us this Kp 0.154. Okay? And once again, to describe what this equilibrium position is, so you can see this is an equilibrium constant. The Kp value is less than 1, but this Kc value is greater than 1. So what does that mean? So that is where this gets a little bit tricky to interpret, okay? So I would say that this equilibrium position is kind of somewhere right in the middle. 4.70 is not like much greater than 1, okay? And 0.154 is also not really much less than 1. So it is kind of somewhere in the middle. And if you look at these concentrations, right, you can actually see that there is more NO2 than N2O4 at equilibrium. So the position is maybe in the middle, somewhere towards the left.